So in this example problem, we're going to use Raleigh's method in order to determine the displacement at the uh, displacement at the end of the beam, and that in order to calculate our function vc of x along the beam. So we're going to focus in on part B of the problem, where we're going to assume our shape function is going to be equal to delta times x over L squared. Okay, so from part A, the video in part A, we talked about how you could calculate the work due to the concentrated applied force, and in this case we said our work was equal to 1/2 p times delta. Alright, so what we need to now do is we need to calculate our strain energy, U. So our strain energy is going to be equal to 1/2 over, from 0 to L, e to the iz times our second derivative of vc of x squared dx. Okay, so um, so if we do all that, so we need to first determine what is vc of, what's our second vc of x, the derivative of vc of x, and then the second derivative of vc of x with respect to x. So v prime c of x is going to be equal to um, let's rewrite vc of x first. Vc of x is equal to delta x squared over L squared. Okay, so it's really delta over L squared x squared. So we take the derivative of vc of x with respect to x. We'll get delta over L squared times 2x. And then if we take the derivative of that with respect to x, we'll end up getting delta over L squared times 2 times 1. Alright, so it's just going to be equal to 2 delta over L squared. Alright, so that's a nice easy number. We can plug this vc prime of x term into our integral. So if we do that integral, we're going to get u is going to be equal to 1 over 2. E to the iz is a constant in this case, so we can take it out of our integral. So we'll get an integral from 0 to L of 2 delta over L squared dx. Alright, so what this ends up being is that this is just a constant, so we can take it out. So we end up getting e times iz over 2 times 4 delta squared over L to the 4th times the integral of 0 to L of just dx, so that's just going to be equal to x from L to 0. Alright, so what we end up getting here is we're going to end up getting e to the iz of delta squared over 4 over 2 would be just 2 out in front, L to the 4th, and then x evaluated from L to 0 would just be L minus 0. Alright, so we're just going to end up getting 2e to the iz delta squared over L cubed. Alright, so we're going to now set u equal to w and solve for delta. Alright, so if we do that, we'll get 2 e to the iz delta squared over L cubed is going to be equal to minus, is going to be equal to, what do we have for w? W is equal to 1/2 p delta. Alright, so if you rearrange all this, what we should end up getting is we'll get delta is going to be equal to length cubed times p over e to the iz, and then there should be a 4 here. Okay, so so this is equal to 0.25 pl cubed over e to the iz. Alright, and then if we remember our delta from our beam theory, it is equal to 0.333 pl cubed over e to the iz. Alright, so we're about, from the actual solution, our approximate solution using this function was about 25%. Alright, so using Raleigh's method, you're going to get It's simple to apply, but depending on the shape function that you pick, you're going to get the error from the original function may be very small, or it could be kind of pretty significant. In this case, we're off by 25%.